All good.
Yeah.
Sorry about that.
Okay, good afternoon again. I am Gianna Cauzzi, for those of you that don't know me. I work here at NSO and I've been active in all this outreach workshop organization, trying to get the students to understand things and so on. So Ivan asked me to describe to you, to give you an idea on how you go about planning observations with DKIST or with any instrument, with any telescope in general. And of course I took a different tangent, and I will get there, but maybe not as fast as some of you might like. So my reasoning was that some of you, and tell me if I'm wrong, might not be so familiar with the DKIST problem. Right? I don't know. I know certain faces here that you might have an idea, you might have seen some pictures here and there, but maybe you never had, say, step-by-step presentation of the main features, the main important characteristics. So at least you're happy. How about you? Do you know everything about DKIST already? No, good. So for the other ones, I apologize because you might have seen it already quite sometimes, and all those other people, and so you have to go through it again. What I try to do is here and there to go back to what Ivan has told you during the previous lectures. So trying to make, to have a thread, a logical thread that goes from what he has shown you to what the telescope is. Okay, so this is the picture that he likes most, one of the pictures that he likes most, because he puts it on every lecture. So let's see if I can point. So it's the telescope is true, the sun is fake, I think, because I've never seen the sun doing that.
Yeah,
some straight Photoshop.
Yeah.
So the telescope is almost finished. It's on Maui, and we are at the DI Institute. And the first science light would be the sun. And I say science light because everybody has seen the first light already. You've seen the images, you've seen the videos, and so on. But science meaning that there will be observations planned to do science, not just to show that the telescope works, but actually somebody will have a science idea and try to go there and do these new observations and see how it goes. So this is the cutaway of the telescope. It's big. I don't know if you can notice there are little men down there. So it's 35 meters tall, right? And we can divide it in three big chunks. One is the telescope itself with the enclosure and the telescope mount. The relay optics that will take the light from the telescope down to the instruments. The instruments live at the bottom part of this big structure, and I will tell you also why later on. So now we start with the telescope itself. So the DKIST is a Gregorian telescope, and I don't know many of you know, but a Gregorian is this thing. Gregorian is a telescope where you have a prime focus, which is the focus of the primary mirror, which is before the secondary mirror, right? So most times, the telescopes are on axis. That means that then the light goes down again along the main axis of the telescope, and so you have to have a hole in your primary, because otherwise you don't know where to throw the light, right? This is, I think, right? There is something of this kind. It is typical of solar telescopes. The very distinct characteristic of DKIST is that it is an off-axis. Yes?
What's the advantage for a solar telescope of using a Gregorian focus as opposed to a Cassegrain?
Oh, to remind me what the Cassegrain is. Let's see. I thought that it was easier to put
It's where you have a convex secondary, so the prime focus is behind the secondary, so it doesn't cross over like that.
Right, I see what you're saying. I actually don't know the answer right off the top of my head. Let me think. I think it was easier to put some control of the heat system.
Or aberrations in the Cassegrain system.
Are aberrations worse in the
Cassegrain is notorious for that, because you have to have a lot of correcting optics on a thing like this.
Okay. But I will investigate. Sorry, I do not know right away. So the big thing of DKIST is that it is an off-axis, right? And it's also extremely fast. You remember that Ivan has told you what the F ratio is in terms of telescope, is essentially the focal length divided by the diameter of the primary. So this is an F2, means that the prime focus is about 8 meters away from the mirror. And let me see if I remember what I have there. So here's some pictures, just to go fast. This is within the enclosure. This is the mirror, is almost vertical to the floor. It would be looking at the sun when it is very, very low, like a few degrees above the horizon. That little curtain, the little super curtain up here is the cover that can be deployed very fast if you have issues, accidents, some strange things going on. And you will see also why that is. And this is sunlight some months ago, and again you have your meant for scale. And this is the primary illuminated, and you can see up on top, the right top, then you have what's called the top end assembly, telescope assembly, that includes the secondary mirror, which is out here, and here is the heat stop, which is a very important part of the project itself. And we get it. So the first unique thing is that it is very big for being a solar telescope. Is about, the largest nowadays is 1.6 meters. This is almost 3 times as big. So with it goes a lot of first, right? One is that you have a much higher resolving power in terms of spatial resolution. And even as described to you how you derive the PSF of a telescope of a certain aperture, right? With the diffraction theory. And so that if you have 2 objects that are separated by that magic 1.22 lambda over d, you say that you're resolving this difference. And of course, the larger d, the smaller is the thing that you can resolve in the sky. In the case of a 4-meter telescope, at 400 nanometers, you have that number 1.22 lambda over d comes out to about 10 to the minus 7 radians, which corresponds to 0.02 arc seconds in the sky. And for the sun, being what it is, that is 15 kilometers at the surface of the sun. So we can resolve that capacity. Of course, it's way to be dependent, so that if you go in the red, that will increase, and this is what you all have seen. So indeed, the resolution is of the order of 40 kilometers at this wavelength. This was almost 800 nanometers. So this is very exciting, because then we want to go and look at all these details, you know, all the details of what magnetic fields do, how do they evolve, or why do they have that spirally thing, why are they like ribbons and not like bright points. And you say, well, I have also large telescopes, so I have a lot of light, so I can do this much better. Is that true? Yes.
What was the question again?
Can I really do better the physics of these things because I have a larger telescope? Yes, no, I don't know.
Depends how small is the physics.
That's a good one. But no, the answer is no. Because you know that the photon flux per resolved element is always the same. It doesn't matter. You know, you can have 10 centimeters, you can have 100 meters. The flux per resolved element is always the same. So if you want to do better physics today by using more light, you have to relax your spatial resolution. You will not work at the diffraction limit of the telescope of that wave. That doesn't mean it's bad. Actually, no, that's what we want to do, right? That's why we have it. But anyway, this is always nice to remember. The sun is a star of 26th magnitude or something, and that's what it is. You know, the light that comes out is what it is. And indeed, but however, something else matters. You know, size matters after all. So here is, do you know how big is the solar image at the prime focus of DKIST? Or do you know how to find it? He has told you. Not too long ago, I say. So is it like this, like a centimeter? Sorry for the ones that are not online, that are not here in the room. Is it a centimeter across? Is it a meter across?
Maybe like 10 centimeters?
Okay, why?
Yes.
You never volunteer an answer because then you have to explain it.
I used to know this.
Amanda says it's about 50 centimeters. It's about 50.
This is about as big as the second degree.
Reason, but maybe not. Nobody else wants to volunteer.
8 centimeters?
It is about 8 centimeters. Why?
Because the f/4 mirror, the sun is about 100. So it's f/4 mirror, which means 16 meters focus.
It's 8 meter focus.
8 meter focus.
Yeah.
The sun is 100 of a radian. So you multiply the two, you get 8.
That is a very good one. The sun is 100 of a radian, more or less, plus or minus 10%. Right? No, actually, minus 10%. So that is always the scale that you have to keep in mind. A focal length of 8 meters becomes an 8 centimeter. So it's actually closer to 7, but just. And I think again that he has showed that Gianna showed you earlier in the series the solar image of prime focus of black mass. It's like a meter large. It's huge. It's beautiful. And so we couldn't get, this helps with the heat control, of course, because you're diluting all your power over a much larger area. But of course, you cannot have a 4 meter that has a 9 meter focal length. It would be a big structure to do. So, how about the power that is collected by the telescope? How much would that be? 1 watt, a megawatt, or whatever. Power,
Well,
energy per time, right?
well,
Watt per, joule per
I think
second.
that would be 1,300 watts per square meter times 4 pi r squared, or 2 pi r squared meters. Or no,
Pi squared.
r squared, where r is 2,
Correct.
excuse me.
Why 1,300 watts per square meter? What is that?
That's the incoming solar flux at the distance of the Earth.
Correct. That is another of the things that you cannot change because the sun is what it is and we are where we are. So that is the kind of light that you get. It's actually, I made the number easier because I would like to, I put it 1 because we are within the atmosphere. There is a little bit of absorption in the atmosphere. So yes, it comes out to about between 12 and 13 kilowatts, which is a lot, but it isn't. It is what I have on the roof of my house because I have solar panels of about 4 square meter, whatever, right? So no, 12 square meters. That's what I get. Because you oftentimes hear, you have to think about this, that there is the power is so strong, that the heat control is such a problem and so on. And you expect that you have like a furnace there that does, if you put something, everything explodes. That is the power, which is a big microwave, but still a microwave if you wish, right? You have a microwave of 2 kilowatts. Big. What?
Unless something gets caught in the heat.
What is the difference here?
Because it's concentrated.
Because it's concentrated, because the area is 7 centimeters times 3.5 square times whatever. So that is the heat load. And the heat load will be that divided by the image surface, which comes out to about 3,000 times the solar radius. Right? And again, don't be fooled. Certainly you don't go there at 10 or anything. No. You would not want to do this. Like hold your hand and try focus. That's not a good idea. But doing this would be okay. And it's something that you could.
I mean, this is still probably much less than a laser.
Yeah, I think so.
So
And
it's more
also, I have a model. I have my exhibit 1. This magnifying glass has a certain power that it is 3 to 4 times less than the DKIST. But not 100 times. Well, can they see me? Or
Maybe they can. I don't know where the camera is.
anyway, I have in my hand a magnifying glass, and now it's cloudy, but any other day it's in my office. You can try it out there and see what you can do. Yeah, if you can burn ends.
Not on living beings, please. Not on living beings.
Anyway, so that is still something that you want to get rid of, because that is, again, not a tragedy, but you don't want your optics to be subject to that kind of heat load. So the solution for these kind of telescopes is that you have to get rid of most of it in two ways. One is that you get rid of a lot of sun. So you have a prime focus, you have this whole image, but you don't let it go through. You put a so-called field stop so that there is also a very tiny portion of the sun that goes through. And all the rest, what you do, you dissipate that heat via that heat stop, which is a thing here at the top end of the assembly. And which is better depicted here. So the heat stop is a piece of metal, essentially, with a hole. Through that hole, you have your field that you will further analyze down the line. And the rest absorbs the extra heat. In this particular case, there is a lot of pipes, you can see down here, that transport coolant that flows continuously, so that that heat is taken away in this manner. The field that the heat stop lets through is about 5 arc minutes over the sun. So the sun has about a diameter of about 30 arc minutes. So it's about a centimeter hole. At that point in prime focus, you have a hole of a centimeter that lets through whatever solar light you will analyze further down the line with your instrument. And that light reaches then the secondary, which is on the top of this assembly. Now it's not maybe not very clear. I think I might. Sorry. So here, oh, sorry. That is, you can see the whole structure up here in this part. So this is the secondary with all the proper things, and the prime focus is down there. Okay. Then what happens? Oh yeah, I forgot to say this. The fact now you can understand why, at least one of the reasons why, the telescope was made as an off-axis. That thing is a big, bulky structure with all that metal, with all those pipes, and so on and so forth. And so that putting that on top of your mirror is something that gives you a bit of anxiety. And so people plan to do it. So I think the European project is an on-axis, and so they must do it somehow. I don't know the details, but they have to do it. That would probably be less bulky than this one, and so on.
But they wouldn't be above the mirror, right? Because the mirror is kind of like almost vertical, right?
Why? No, the mirror, the position of the mirror depends on where the sun is, right? It can be vertical when the sun is low, but then when the sun gets high, the mirror turns around and becomes almost horizontal. If the sun is at the zenith, that's what happens. So yes. Oh, I see what you're saying. Yes. Yeah. Oh no, a great part of the day would be, aiming at the mirror below. So that's not going to be very prudent, I would say. So that was one of the main reasons why they wanted. It's got other drawbacks. For example, it takes up much more volume within the enclosure. But this is one of the most important things. Yes.
Do you lose information by this heat stop because you're blocking a bunch of sunlight?
Well, you're losing 90% of the sun. Yes. No, 7 or 50. Yes, but that is the goal of an instrument, of a telescope like DKIST, is that of looking at things that are of a small scale on the sun. And if you have a small scale, you cannot have a large field of view. The two things together do not. I mean, you could do it if you had
Huge.
proper optics. You have to enlarge your beam enough to afford the spatial resolution, because at the end of the day, your camera has a pixel, which is 10 microns, right? And if you want to put all of the sun at the 0.02 arc-second resolution over CCD, you need a CCD which is as big as this room, and all the optics that go with it. You know, the larger the telescopes, unfortunately, the bigger the problem becomes that all the optics scale, so that you have to have lenses that are just large. Not more than a meter regardless if they make them, but yeah. So yes, you do lose information. You're throwing away a lot of your light. Yeah.
So I guess how is that different than having just a smaller mirror that focuses only that much, like through the?
No, because the resolution, the spatial resolution depends on the diameter of your primary.
That's right.
So you it's not the field of view, it's the resolution that depends on the primary. Right. So you cannot afford that resolution with a 10 centimeter telescope.
Yes, so always keep in mind that sun is an extended object. So we are never collecting the light from the whole sun and putting it together and then cutting 90%. We are cutting away 90% of the image. So we are focusing on the 10% of the image that we want.
Yeah.
Right. So that's the point. And the primary reason always for making bigger telescopes is to have less diffraction. Basically.
Yeah, or compromise that, but having much more light.
But having more light.
To do a more fine analysis of colorimetry.
Yeah, but in this
temporal
case,
resolution.
having more light means having more light per our sampling element. So remember that at the beginning we were talking about sampling elements and how, you know, bigger telescope for fixed sampling element gives us more light. The fact that the optimal sampling element changes with the size of the telescope is this story that Gianna told you about the number of photons per resolution element always being the same. But you are never prevented from, you know, spoiling that a little.
Okay.
Sorry.
Yes.
Question off of that. I'm not as familiar. Are you saying DKIST is 5 arc-minute field of view? Is that what this
That is the largest you can get at
Okay.
once.
Okay.
You can mosaic, you can move, you can point the telescope wherever you want. You know, you can point it here now and then next,
Yeah.
next. But at once, that is the largest you can get.
So from Earth, isn't the sun like half a degree?
Yeah.
So that's 30 arc-minutes.
That is, you know, that is the blue thing.
I'm
is,
trying to, I'm trying
not-
to get, how do you get 10%? Because it's like
oh, I don't know.
35 divided by 30, that's 1/6. So,
You are correct. So it's 1/40th. Yeah.
Oh.
Of the light. Yeah.
okay,
It's a 1/40th of the area, right?
yeah. So it's, okay, I see.
Yeah. Sorry, I went with
Order
the
of
number.
magnitude.
Yeah,
That's
I went with the number. It's a large
Sorry.
fraction. Yes.
Mm-hmm.
Okay. Another good thing of having an off-axis is that you improve your PSF of the telescope. And again, Ivan has discussed how this comes about when you have a circular aperture, that you will have spurious elements in your PSF that are due to the presence of both the obstruction, because you have something on top of your mirror and you have another, then you have a shadow, or you have a hole in your mirror, so your actual surface area is less than, and it's got also some funny shape. And then you have the spider, what we call the spider, which is the thing that keeps that secondary up there, right? It needs to be there. So that at the end of the day, the PSF is much more, how would you define that? Less ideal.
Yeah.
So it introduces, it effectively reduces your spatial resolution because it introduces fringes of all sorts. So that's nice if you have an off-axis. Of course, you pay, somehow you have to pay. And the fact is that the optical aberrations are larger, including particularly the coma. It's one of the issues of the off-axis. Although you can mitigate that with choosing a small field of view and also the focal lens later on. One other important thing here is written, is not displayed, is that if you don't have a spider on top of and the secondary on top of your primary, you reduce much the scattered light because you don't have any metal that can reflect and then bounce and then it goes back up to the primary and so on and so forth. And this is fundamental if you want to do weak signal physics, in particular the coronal physics, because the corona of the sun is very, very weak. And studying it so requires extreme measurement, including a very tight control of the scatter light in your optical system. Okay, so going further down the train of the light, you have primary focus, heat stop, M2, that sends out the light to the Gregorian focus, right? That is the place where you have a lot of your facility optics and calibration things. Here you can put all the polarization optics, and Amanda knows a lot more than I do on this. Do you work up there? Do you go? No? You put the polarization calibration optics. You can put more field stop. Back to, what's your name? Question?
Maurice.
Maurice, back to your question, Maurice. Here you can put further field stops that actually reduce again the amount of light that goes down. And you can also put occulters, going back to the coronal physics. Since the corona is very weak, one thing that you do from the ground, you try to create an artificial eclipse. So that you position, again, a disk of metal that covers the image of the sun all the way to the limb of the sun, and you look at what's above. It works to a certain point. This is the idea, right? That you would have, this will be your image, this is your 5-minute field of view, and the dark thing is your occulter that is blocking the disk, and so it blocks most of the light, the glare. And with your instruments, you can go and look at the coronal features. Whether there are hot coronal features, medium-degree emission lines, or whether they are like more chromospheric features, like speckles and those things. This is the idea of an occulter there. Of course, to work well, your scatter light needs to be low. And so I went fast here, but this is also, you were here for the Valentin's lesson where he described all the polarization measurement, and in particular how careful you have to be with your calibration of your system. And this is where you put all your calibration optics. Questions? I'll get there. I'll go faster now. Another important part is that now you have the telescope and all those things I've been showing until now that do live up here in this upper part of the telescope, but the instruments live down here. And so you need further optics to send out the light. And for DKIST, and this is a first, is that everything is done with mirrors and not lenses. And that means that you are achromatic, which is very nice, but also that you transmit the far infrared. So in principle, the telescope can access all the way to 28 microns. I don't know where the 28 microns come from, actually. I don't know why that. It might be something intrinsic in the properties of mirrors.
It's the atmosphere.
The atmosphere?
It's an atmosphere.
Okay. So and then you're going to the radio window after that. So yes.
What's the interesting size? 20 micrometers. Has anybody looked at those wavelengths before?
That far, some very sporadic things, some people from planes and so on. And there is all sort of lines out there, really. Certainly, your spatial resolution is not good, not at all. So you have to find some particular good physics to tell you, like a bit like ATMA, right? You go into the millimeter. The resolution is not great, but you have a clear diagnostic temperature. Here, they were using some of the higher hydrogen lines. I don't even know the name, Photo Sirius, those guys all the way up there, as diagnostic of electric fields in the corona, because they will be sensitive to electric fields, both in the polarization and I think also in the broadening, right? And so those could be very interesting. Currently, the instruments don't go above 5 microns. The instruments that we have nowadays don't go above 5 microns, but in principle, we're good. These relay optics, besides being neat and
Could you actually beat thermal noise at 30 microns?
That's a good question during the day, so I guess you have to be very zealous with your cooling things. Yeah, maybe that's why this is one of the limits.
Could you sort of mention or describe the air knifing technique that happens? I only recently heard about it, that because apparently, I mean, in order for the light to reach the objects down there, there needs to be an opening.
Correct.
But why is there an opening if you need it to be thermally controlled, a thermally controlled room? So could you explain how air knifing successfully keeps the pressure stabilized?
So what they're saying is, and we'll get to see, maybe not that detailed, but so the instruments are down here on this lab that I will be describing in a minute. And here at this level, there is indeed a hole in the ground, right? Because the light has to go through. That would be the obvious place where to put the lens, because that would thermally and pressure isolate the two environments. You know, the fully open environment, well, almost fully open environment of the upper telescope, and where the instruments are, where you want everything to be stable as much as possible. So the choice was not to put a lens because of the idea of going further into the infrared. And so there is like a hair dryer that pushes air here. So it's like a fan that pushes air at this level, at the ceiling of the instrument lab, that creates a very laminar flow, so no turbulence introduced by that, in principle again. And that effectively isolates the two, you know, it works to keep the two things disjoint. If you want more details than this, I think I'm not the person to talk to, but there's a lot of mechanical engineers here that we can introduce you to.
That was helpful.
Yeah, that's the idea. So, and you know, they've tested it on the computer. The computer it works. Now they are testing it in real life, and we see how that goes. Hopefully, good. I mean, all the thermal control has been modeled. But that was a choice made at the very beginning of not putting lenses. So, and then obviously you had to do something to isolate the two things. Another important thing that this relay optics does is that of creating a Coudet focus. A Coudet focus is a focus which is created by a series of mirrors properly positioned so that the focus itself does not move when you move the telescope. Because this is something which would be fairly cumbersome if you have an instrument, right? Either you attach the instrument to the telescope and you go on from there, or you have to somehow arrange for this. So the various relay optics that are here after this little ball here is the Gregorian focus. So at 3, 4, 5, and 6 all combine to rotate the image and the light so that the focus is actually here. This is the focus, and it is there. It is always fixed. That allows you to plan for your instrument, which is, you know, this is what you do for solar telescopes, because our instruments are bulky and have a very long focal length, so they are, you know, they take up a lot of space. So this is the Coudet lab where the instruments, so Coudet lab because it's a Coudet focus, right? And so that's where the instruments live. And it is a platform of 16 meters diameter, which rotates. Why does it rotate?
Because you can't use all instruments at the same time. So if you want to choose,
no.
Which one?
No, the instruments, you can use them separately or together via wavelength discrimination. So you send the instruments are all, I'll show a picture. The instruments are all in this platform, and you direct light to them via optical elements. But that platform rotates all the time. Do you know why?
Because the sun is moving through the sky, and the telescope has to reorient with the telescope, right?
Yes, I don't know. I think that you said the right thing. I'm not sure if I would have used the same words. The center of your field of view is fixed, is that could be focused that we described. But the image, the sun is an extended object. And so as it moves in the sky, not because the sun moves, but because we move as we do, the orientation of the image changes. Right? It's like looking at a constellation very early in the night or at midnight. They change. And the same happens for the solar image. And so you have to compensate for that or not. You can accept that and have an image rotating onto your detectors. That is cumbersome for other reasons. For imaging instruments, you could probably do well. For a slit instrument, where you have only that sliver of your image, that might not be the best. Right? So that's the reason. It essentially keeps the orientation of the solar image constant with respect to the instruments.
So it's more that it rotates rather than it just moves.
Rotates,
Right.
rotates, yes. So if you start looking at sunspot that it is like this now, in an hour, not an hour, 3 hours will be like this. Okay. Now we finally go to the instruments. Sorry. So again, this is one of the favorite words, I think, of it, like multi-wavelength, multi-high diagnostics. Yeah, I looked at all this lecture before I prepared this one. So at first light, there will be 5 instruments. They're all called facility instruments. They're not private. Everybody will be able to use them if they want to use them, right? They are complementary in the sense that there is a mix of wavelength coverage, of a way to look at the sun coverage, and so on. Certainly, there is an emphasis on polarimetry. That was one of the very, the big priorities of the telescope itself. And since you've done a lot of things about adaptive optics during this, all the instruments apart from one, which is the cryo-NIRSP here, this one, are not fed by the AO system. The actual reason, I'm not sure I really remember. They didn't want to take away, well, the cryo works in the infrared only. It's a coronal instrument. It's optimized to do corona, so weak signal. And it works in the infrared. The AO works in the visible, so they're already, I don't know. The idea is that this instrument, the cryo, will never work a diffraction limit. It would be the one that uses your telescope as a light bucket rather than as a very unusual. I will describe some, not all, because it's way too much, but at that page there is everything and more you want to know. In any case, I'm almost there. So these are the things that you will use to do the slice and dice that he has shown you already. The intensity, the spectral dependence of intensity, the polarization, for example, this, the spatial distribution, and the temporal distribution, right? Temporal evolution. These are all the things that you want from your data. But then again, you are bound by physics, and what we have is 2D detectors that, unfortunately for us, are not wavelength discriminant. They just get light, whatever. Right? It's not like a film, the color film of the 70s, right? That those had some sort of wavelength discriminant in itself. So you had a 3D image at once. Here you don't. So you have a 2D image. And so the main philosophy of these instruments is what, maybe I can do this later. Oh, sorry, I can show, yeah. So the main philosophy will be how do you go about and slice your hypercube? You can decide to do it one way or another, giving emphasis to one thing or another. So this is your Fabry-Perot instrument. He's told you everything about how they work. About the interference works in that particular case. And there is one instrument which is called the VTF, visible tunable filter, which is of this kind. The other one I put in parentheses is a visible broadband imager, is again uses interference, but it doesn't tune. It's not that you can sample wavelength in a fine way. You can sample wavelength with big jumps. Also jump. Anyway, the other philosophy of instruments is the one that uses slit spectrum. So you use a diffraction grating, and you have just one slit that isolates some of the light. You do so because you don't want to confuse space and wavelength, right? So that you have the spatial information in one direction and the spectral information in the other direction in your 2D detection. So there is two instruments of this kind, the visible spectropolarimeter and the cryogenic near-infrared spectral polarimeter. And then there is the one that wants to do everything, right? Which is the integral field unit, which again, it's a bit of a trick because they sell it as the best thing of the whole water, but at the end of the day, at least the one of the DKIST, the DKIST, is a fiber-fed spectrum. So it's the same as before, it's a diffraction grating-based spectrograph. Instead of having the spatial information being just long and thin, you take a small field of view and you rearrange all those pixels and put them along the slit, and then you get the slit like before. So even I have a note, this image is not correct.
Yeah.
Because with this kind of instrument, if you want to keep a decent spectral resolution, you cannot cover all of that field.
Yeah, you can only look at one of these.
You can only
small-
look at one of those little things.
Yeah.
Right. So in that sense, it's a beautiful idea, but just you pay a price because the field of view is small.
That's why DLNERST has two field of views that it can use though, right? It has a small one.
It
and
actually
a
has
larger
three. Has three. So the DLNERST, let me go back here. It's this instrument down here. It has a clever way of changing the optics so that it changes the spatial scale at the detector. So you can go very high spatial scale, small field of view, medium spatial scale, field of view, very bad spatial scale, and larger field of view. You know, you have to pay the price somehow. And that's something you should remember always when you try to do observations. You cannot have perfect. Right? And this is actually a picture of what the field of view of the different instruments will be. So here you have to think of your science. What do you want? You want to have a large area of the sun under scrutiny or not? Or why? So note that the yellow is the square 2x2 arcminute, which is the typical thing provided to the instruments, apart from cryo that will have the larger field of view that we run. And the others give you the instantaneous field of view of each instrument itself. So for the imagers, it's a square. For the spectrograph, it's a slit. For the DLNERST, it's a small square. Don't get fooled when you point at the sun, all the instruments point in the same position. I just put them separate here to see how they compare one another, but they all look at the same. The center of the field of view of each instrument is the same. Okay. What is your favorite instrument? Huh?
DLNERST,
The DLNERST, why?
because IFUs are really cool. The way they're put together, all the fibers is really interesting, especially for DLNERST because all the fibers have to keep the polarization the same because you don't want your polarization changing in your fiber.
Oh man, I didn't even think about that.
Yes.
Otherwise, you're not going to get your signal. So the DL is really cool.
The DL is really cool. My favorite is like something like the DKIST. I like large field of view. So anyway, so here I don't know exactly how much I should go into details. I don't think I want to go into the details. The general sense is that each instrument is optimized for a certain range of wavelengths, for example, or for a certain spatial resolution, or for a certain polarimetric precision, and so on. If you want very high polarimetric precision, go with the spectrograph. Right? If you want decent polarimetric precision, but larger areas, go with the image. in particular with DDF. This one I will use for the next example, so let me say a few things. One is that the spectral range is fairly limited, so you go only in this between 520 and 870 nanometers, right? So if you have a favorite line that's not in that interval, too bad. You have to do something else. And actually, I have something at the end about that. That if you want to do a spectral scan, you have to sequentially step, right? To build your, in this case, your spectral line. You have an image and you have to build a spectral line. So you tune different wavelengths. And when you do your science, you have to be aware of how long it takes. Because if it takes a minute, it might be a bit too long, especially at this resolution, right? The spatial resolution. Because if you have something small, it evolves fast. And you want to have all the spectral information fast. So you have to tune fast. If you do so, what happens? You don't have enough light. And so you don't have enough signal and so on. It's part of this compromise. Some important things that will come out later is, for example, the scale of the pixel, the spectral resolution, and so on. Some of these instruments, most of these instruments are fixed. You know, the spatial scale of that instrument per pixel is what it is. You cannot go and change the lens every other day and change. Apart from the DL-nurse, but it has this little trick that has 3 different configurations. Right? Spectral resolution, we can discuss that. For the interference filter, is essentially fixed and wave independent. For a diffraction gradient spectrograph, what do you think? You've seen all these lectures. Is it fixed for a given line or not? No. Yes. One says no, one says yes. Why?
Because the separation is given by how thick the slit is. The separation in the lines.
Yes, the slit width influences the spectral resolution. Yes, is correct. Already, you could change the slit width.
Okay, it's hard to do though.
No, you do it. For spectrograph, you always have that option that you can add. The slit is usually, what do we call it in English? Jaws. The jaws, right? It's two metal places that get close or further away and create the slit jaw. Yeah, the slit jaw is what is reflected by the slit jaw, as the image of the slit jaw. It's actually a slit jaw image. Now that I think of it. So that is one way how you could change the resolution of the spectrum. There is another one, and he's been showing you a lot what happens when you diffract all that light. What happens? What kind of transmission do you have? Do you remember all those things that move one from another, I don't know if I have a figure.
You're talking about the orders?
I'm talking about the orders. So you could choose a different order for whatever reason you decide is good for you, right? And so if you go to this order, you have a certain spectral resolution. If you go to that order, you have a different one. And also you have a different intensity. It's complicated. It's really, in a sense, the interference, the Fabry-Perot waves and so on, from this point of view, are easier. They are more salient. Anyway, so this was the same for the VISP. The VISP is my other example because there are two opposite kind of instruments. And this is what we were saying. You can change the slit size. You can change, it's actually very, very versatile. You can pick 3 spectral ranges. Any 3 spectral ranges within the visible, going from about 380 nanometers all the way to 900 nanometers. So you can decide, I want a line in the very blue, I want a line in the yellow, I want the one in the red. And I go, no, I want 3 lines in the red. And so on. And so it's very versatile in this sense. It's very flexible. It probably will go on for 20 years, and every day there will be a new idea, right? At the same time, you have to pay a price. So it might not be the best efficient thing for doing what you want to do. And, you know, depending on how you combine your ranges, your spectral resolution might change completely. You have this, you don't change the slit, but today this line has this spectral resolution and tomorrow it's got maybe a factor of 2 less because I'm coupling it with other lines, and that means that I'm using different orders for this, for that, for that. So there's a lot of flexibility. Okay. I think that now we're ready for doing an experiment. So how would you, I mean, I gave you the solution here, but how do you plan an experiment? Because I think at the end of the course, you will want you to do one. So you better start thinking. Anybody has planned observations until now? No? Oh, how did you do that?
Well, if you have a problem in mind,
Uh-huh.
you try to come up with a way to test your problem and refute the hypothesis. Then once you have the idea of what you want to measure, you go to the telescope, you start thinking about telescope can measure.
Yes.
And you try to figure out what's the closest thing you can get out of your data that's helping you refute your hypothesis or not.
Okay.
And then, and then use the IPC for it.
There is a lot of hidden knowledge in what you've said, right? I mean, in a sense, that is the scientific method. You have an hypothesis and you try to test it. So how do you test it? I mean, you have to know that that certain line is good to provide you an information of the magnetic field or whatever. You have to know that to get that information, you need the polarimetry to a certain level of precision, and so on and so forth, right? You have to know that you need the temporal discriminant of a second, 10 seconds a day, right? So there's, again, a lot of these things that go into planning your observations. It's not trivial by any means, especially if you're new in this. But so this is what Momo said, pick a physical problem, think what are the most important characteristics to go about that problem. So do I care more about the large field of view, the spectral fidelity, and so on and so forth. Then decide what is the instrument that's best for you. So then you go, you know what the instrument does, and you say, how long will it take me to get data? Is it enough or not? No. Okay, repeat. Go back, and so on. And then at the very end, we'll use some more sophisticated tools because you cannot do all of this by hand. Some instruments are easier than others. You could do it by hand, you know, with a piece of paper, really. Some others, like the DKIST, are very difficult because it really depends. There's a lot of interdependencies. So this is my use case, and I want you to do the numbers for me. So, right? This was his lesson when you had the intensity of the sun emitted at that wavelength. And so I didn't specify any instrument, which is 2.2 × 10⁻13 in SI units. And I went through the problem and I said, it doesn't work, and so on and so forth. And then I looked at the lecture and you had the angstrom versus meter problem. You know, the units are important. So the number of photons can be written as the total energy divided by the energy of a single photon. And so you do your math, you have intensity, you have, what is the delta sigma? Do you remember what the delta sigma is? You know, the intensity is an energy per unit area, per unit solid angle, per unit wavelength, per unit time, right? So some of them are easy enough. So I is our intensity. This, what do you think it is? Is delta of big omega.
Solid angle.
And what number is that? I mean, not in 10⁻⁻, I don't remember what, but what does it describe?
The area on the sky. So it's some, well, there are two ways that you can
Define it. So
Yeah.
you can either define delta omega as the solid angle of your resolution element and delta sigma as the area of your telescope. Or you can define delta sigma as the area of the resolution element on the sun and delta omega as the solid angle of your telescope.
Correct.
From that distance.
From the sun. And I think that even had used the second definition. So I'm following his notation here. So the delta omega is actually the solid angle subtended. Do you say so, by the telescope from the sun, at the distance of the sun. Delta sigma is the area of the sun that is emitting that you care about, and of course it depends on the size of your pixel at the end of the chain. Delta lambda is your spectral resolution, essentially your spectral interval. Are you integrating over 10 mini angstroms or over 3 angstroms, like some of these instruments do. So that counts into your energy, and of course delta T. That's how long are you integrating for, right? So if you did this for, and again, following his example, you have 4 × 10⁸ photons. That's nice. That's a lot of photons. Why is that? Because from Kevin, you've heard that when you read something, you can go back to the number of, if you read a camera or detector, if you go back to the number of photons, and if you assume that the readout noise of your camera is negligible, your noise is about the square root of your signal. And so here we have a signal to noise ratio of 2 × 10⁴, which is huge. It can do a lot of very nice spectroscopy, a lot of very nice spectropolarimetry, and so on and so forth. So, very, very nice. Everything happens. We can do everything, right? Of course. Then, so you start very nice, and then you take what you can. So now the VTF, not any single instrument. The VTF has got several issues. So not only the VTF. One is the telescope. It's not 100% transparent, right? I mean, we're not doing badly because mirrors are good, better than lenses as well. But still, you have a lot of mirrors before you even start the instrument. So there your transparency goes down by a factor of 2. Then what comes?
So does each mirror really only have a reflectance of 0.9? Or is that
There's
just
a lower
like
limit. It's actually, I don't know the exact numbers, but it's not too far from there. 0.95. So yeah, you don't get to 0.9. So, what else is not 100% transparent?
The atmosphere.
The atmosphere. Well, actually, I think I did not even consider that, but yeah.
the pre-filter?
All of your instruments. All of your instruments is not 100% transparent because you've got a lot of mirrors and a lot of lenses. There are lenses. In the instruments, you do have lenses. So for the VTF, the total transparency is 0.38. That becomes 0.19 in polarimetry. Why?
Because you're doing dual beam, so you split it in half.
Correct. They split in half the light, and they have a dual beam. So each time you acquire something, you have one state of polarization, and it's orthogonal at once. Right. So the light is split in 2. And 0.38 is huge for an instrument. It's huge. Spectrographs are much, much worse than that. Why? Again.
Because of the slit.
Because of how you distribute the light. If you remember the conversation when we had, you have 100% transmission at the proper wavelength, you have 100% transmission light of the Ribero. Then of course you have all the elements before and after and so on. But that is the throughput of the Ribero spectral. It's huge with respect to spectrum. Spectrograph, you distribute the light in 1,000 order, right? So of course the first few are important, but still, you're really splitting your light, you're wasting your light a lot in the spectrum. So then what do we have? Cameras are not 100% efficient. They actually have a very strong wavelength dependence often. In particular, the one that the VTF will use has 60% efficiency at this wavelength. You know what that means? Explain.
60% of the photons that hit the detector will create an electron hole pair.
Correct.
In the silicon.
Mm-hmm. So there you have another 5.6 that you have to take away, right? So now your through number of photons comes down to 4 × 10⁷. So signal to noise is 6 × 10⁵. Still very, very good. But as usual. The numbers that we had used were, if you remember, taken from there, but I've put in red the things that do not change. cannot change. The sun cannot change. The energy of a single photon doesn't change at that wavelength. My telescope, it is what it is, right? The blue ones are the ones that are more instrument specific, if you wish, because I decide that my pixel in my instrument is this much, or that much, and the same for the spectral resolution. And the only lonely left is the delta T, which is really what you play with, what you want to do, signal to noise counts.
You can also play with delta sigma for, at least for an imaging thing like this, where you can bin pixels together if you don't care that much about spatial resolution.
Yes, but actually here it goes the other way around, and we get to your suggestion because the numbers we have done were for delta sigma equal 100 times 100, right, kilometers. The pixels of ETL are 10 kilometers on the sun. So there you have a factor of 100 and you go down right away. Yes.
Likewise, you can use a wider filter.
Yes, but at that point you have less spectral information.
Right.
Yes, yes, indeed. The delta lambda is 0.43 and it was 0.01 in our original calculation. So you take away 100 and you give me 3, right? Another big plus, the delta T, we had counted 1 second. These instruments don't expose per second. They expose for milliseconds. Why? 25 milliseconds in this particular case, yeah.
No, because you need to be able to remove the effects of atmospheric C. You need to be able to speckle reconstruct.
Correct.
Whatever.
That is a big constraint for the imaging instruments, right? So, and actually, yeah, if you want to keep your high spatial resolution, if you didn't have that, it would be useless to have a 10 kilometer pixel, honestly. But we can go higher than that. Okay. So that's a big one now. And also, so now we go down in number, right? So we're counting that each photon is at 1 electron, and 1 electron is a photon. And so our number, signal to noise per single exposure for this kind of instrument is 200, right? So we have to work somehow. Another important thing, which is related to what Ryan was saying, is that actually an upper limit on the exposure time is given by the cameras because they saturate. After a certain number of electrons, they saturate. The electrons start spilling all over and you don't know what is saying. And the cameras that these guys are using saturated about 80,000 electrons. They actually, I think I have it here, they're actually very nice because the readout noise is almost zero. It's amazingly low, right? So you can also expose for very little and a very low signal, but then your noise is not so bad that you cannot just do that many times and integrate and not being too effective. And then it saturates at about 80,000. So the signal to noise ratio of a single exposure at the very best is 0.0400. That's what you can. Is it enough for you? Okay, well, fine, let's go home. If not, you have to do other things. You remember, for example, from Kevin, that the noise regime, so what I was telling you, that in that camera, this read noise is always very low. I don't care too much. And so as your signal goes up, you really approach fast at the short noise of the photons. But also you can increase that much more by integrating more exposures. Right? Or as Jonathan was suggesting, we can bin. We can get rid of some spatial resolution and have more numbers. And I think that now I wanted, do we have time to do a 10 minutes exercise? Did you download the IPC of the DKIST? Yeah? Does it work on your computer? No? Well, we can do it here. It's a standalone Java thing, so it should be fairly. So when you open it, oh, sorry, here I have the thing. So. Make it bigger. So this is the interface of the IPC, and what are the basic things? So there is only a limited number of lines that you can choose. because this is an interference of a Ripper instrument. You have to isolate the order, right? Because you have a periodic transmission, so you have to isolate the order, and then the free spectral range is not very large, so you have orders are separated by a few angstroms, so you have to have rather narrow prefilters. So essentially, for each line that you want, you need a prefilter. Prefilters are expensive and cumbersome to fabricate, and so the instrument only has a few that you can see here. So if you go here, you can see there should be a menu that comes down. Does it? One.
I think you need to go to basic or advanced.
Oh, no, that's okay. That's the same.
Okay.
How do I? Here, reset. It will come back. So here, yeah, there you go. So you can say the sodium line, the iron one. This is a mid photospheric line. This is a photospheric line that Ivan has shown you many times. You do polarimetry with it. This is a chromospheric line, H alpha, and this is another chromospheric line. And these are the filters that are currently available. That's it. So we go with our favorite line, which is always the photospheric one, right? And you have a default mode. This will be your default mode. The default mode is to, I don't know if you should use the cursor or not, is to have a sampling of the line in 11 points, -5 and +5 on each side of the core of the line, which is defined. It's defined up here, central wavelength. The actual steps, the spectral steps for each point are also defined. 3, this is 30 milliangstrom, I think. Yeah. And then you're doing as a default, you do polarimetry. That's what they say as a default. And so you have 8 acquisitions. They have a 4 modulation state scheme, and they repeat, right? So if you do all these numbers, going to what I was telling you before, you have a signal to noise per exposure, which is 600, almost 700, right? And it takes you 12 seconds to go through this line. And each image is exposed for 25 milliseconds. So hopefully you'll be able to do your reconstruction. So now, assuming that you can, then you keep the spatial resolution given by the wavelength, because at that point it's given by the wavelength. This is your default. Is 12 seconds too much for you? Is it too long, too short, too long? Or is a 667 not enough? Or maybe you wanted to see something else in that line that required a larger scanning. You can change all of that, not in the default mode, because the default is default. So I go to the advanced, it asks you, are you sure you want to do it? You say, of course. Nothing explodes, even if you don't know what you're doing, nothing explodes. So, right? And at this point, you can change a lot of things. All the yellow things can be changed, also the white. For example, for Jonathan, we can bin. I don't want all of that resolution. Actually, let me go to 4x4. And that should change what happened. Why did this include? It should have included in there. Oh, okay. No, each one is still 667. That doesn't change because I haven't changed. Let's see. They changed my exposure time because apparently I was probably saturating. Right? And so they do it automatically. Say, well, if you do beam 4x4, I got too many counts. I cannot do it. So okay, go down. So what has effectively improved is that I go faster. I go 2 seconds instead of 12 seconds. You could change the number of steps that you want to use. For example, 8. You can do that, -5 and +8 because whatever, right? And so then you have your total acquisition time loss and so on. All right. So what do you want to play? I mean, is the game clear enough? Essentially, what they're doing is we don't see anything, but they know about the solar flux, the transmission of the atmosphere, Actually, all of this software assume at the beginning that you are at the center of the disk, so that you have the maximum counts you can have.
In the quiet zone.
In quiet zone, yes. Yeah, if you were in the spot, those numbers would be much lower, but this thing would not know about it. I don't know whether you can probably change that, the level of light. Then they assume the transparency of the telescope, of the instruments, including or not the polarization analysis. The camera, the noise, and all of these nice things, and then they do the math inside, which in itself is not too different than what I've showed you before. Right? It's just more cumbersome to do it all the time. They just convention it for you. You can put up a sequence of different lines, right? So this means that you will do first one and then the next, and then you would repeat if you want. So while this one, since we've been 4x4 took 2 seconds, this we kept it as it were. It takes 28 seconds because it's a broad line and you were sampling it overall a lot of points, 25 points here. And this is the signal noise that you get. You can, what can you do? You can iterate, you can do 10 of this and then 1 of that, and so on and so forth. Yeah, it gets complicated fast. And at the end, here it tells you how long is your final sequence. You go for an hour and you have that.
And it even tells you how much data volume will be.
Yes, you don't want to look at that. This is the most voluminous instrument because VPI, VTF, and the NURSP for the visible part, they use the same cameras. And the default that they go at 30 Hertz. They are 4x4K and they go at 30 Hertz. So in itself, that is already a data volume that runs, right? VPI, at most, you can have 2 channels. 1 camera, 1 camera. This one, in the default mode, has got 3 because it has a dual beam. I don't know what you're saying it, but it's not in the same detectors, 2 separate detectors. And the reference channel. So it's 3 of these things going at 30 Hertz. That's a lot of data. The cameras don't tell those people there, but they can go much faster than that. If you isolate a small region, you can go 50 Hertz, 100 Hertz. If you want to do something fast.
Yeah, I'm just reading the specifications. You can go up to 1600 hertz.
If you isolate a very tiny, yeah. Yeah. So these are the newest cameras of Andor that has developed. Actually, they developed it for us. Now they're selling them to all the, because they're very, very low noise, so they can do also weak nighttime galaxy things. So, but anyway, yes.
The beam being useful?
The reference channel, the broadband channel. So you have the Fabry-Perot that tunes, and you select the wavelengths, or for example, those wavelengths there. Mm-hmm. The dual beam, means at some point you split the light and they go to separate detectors. And then the third one is independent. It's the same image, the same solar image, but in a broad filter and no polarization. It's just a continuum reference. It's what you use to do the speckle. You do it there and then you apply it here. That's what Kevin, I think, showed you. There is another IPC also for the other instruments. This is, for example, is the one of the DISP, and it's much more complicated in a sense because you can change everything you want. So I don't think I want to go into the details of this. If you, for his exercise, need to do something, come to see me, we'll do it together, we can discuss it and so on and so forth. But let me think what that is. Can I move this? Yeah. I had homework. I had homework for you. Who was at the seminar by Francisco Iglesias last week? You were there. So Francisco was a visitor last week, and he is one like Valentin. He enjoys polarimetry very, very, very much. He likes to study phenomena where the magnetic field is extremely low, extremely small, And so the actual polarimetric signal is very, very, very low. So you need a lot of care in getting that. And you need a lot of photons because he gives us his requirements that are this in blue in this slide. So he said that with a spatial resolution of a 0.1 second, he would like to get to a signal of about 3 × 10⁻⁴, which means that the signal to noise is 3 × 10⁻⁵, right? He wants to use this line because it's the line that shows what he wants to see. It is in the blue, 4600 angstroms. He wants a spectral resolution of about 20 milliangstrom because the thing that he wants to see are only in the core of the line. The core of the line is tiny. And finally, he wants to go fast because these things evolve like you won't believe it, right? So those are his requirements. To date, nobody has been able to do anything of that kind. I mean, right? I wrote what people have been able to do for this particular problem, right? So they got that signal to noise, yes, but they integrated over 200 seconds, not 10. They had a spatial resolution of 0.4, not 0.1 seconds. They had a spectral resolution of 60 milliangstrom, not 20 milliangstrom, right? So you get an idea.
Wait, what?
Yes. So what?
Wait, what was that? With what instrument?
Oh, there was a special custom instrument. It's called the fast solar polarimeter. They developed by the Max Planck in Germany, FSP. So they're very, very fast camera.
Yeah, but FSP is just the polarimetric part. I mean, in this one, I think
The
it
cameras,
was.
no, also the cameras.
Yeah, the cameras also. I think this was.
Oh, the spectral discrimination was done with the Fabregaro at St. Peak. And they didn't scan the line, it was just one wavelength point. And the spatial resolution was given by the telescope, which is 70 centimeters, and how fast they went and how well they used the reconstruction. You know, whether the calibration is polarimetric. Right? Only assume perfect calibration.
And they removed one atom, I think. I don't know if we are supposed to say that.
Everybody has this idea that it was IBIS. It was not. It was not IBIS. IBIS doesn't work in the blue. IBIS is coated from 5500 to 8600. It was one of the Fabregaro of St. Peak. They used the controls of IBIS to tune the thing and to do whatever they had to do. But because they also had another line together. But it was not the IBIS. They just used the control software. So he would love to do that. And he came out and said, can you do that with DKIST? So this is your homework. Can you do it? And I think I've given you everything you need. You know, I don't want you to go through the IBC because it's complicated and so on, but I've given you everything you need. You know, how well the camera, oh, okay, why the vis? Because it's the only instrument that works at those wavelengths that does polarimetry. All the others work further in the right. So the camera, how well it works. The instrument transmission of that wavelength. The modulation efficiency, because you know, you've seen all the lecture by and so on. Camera duty cycle means how much of my time am I acquiring versus working versus how much do I spend in overhead and other things. The pixel size, spatial and spectral. You can choose the slit. Given your thing. That's a good point. Actually, no, this is wrong. This corresponds to the 0.1 slit. The 0.016 angstroms correspond to the. No. Scott. That is the spectral scale. It's not the spectral resolution. That is the spectral scale for this particular quarter. And I think that's all you need. So what would you do? I mean, you have to know some other things, but
it's a good homework.
do you want it for tomorrow, for a month? Or
No, yeah, I will just type it in their homework, so it will be. Yeah, you have some time to tackle this.
assume that the camera is perfect and doesn't have any radar noise, just the numbers, the photons that you get are the number, the counts that you get, considering the quantum efficiency. without noise, scrap that. So you don't care also of saturation. I didn't tell you anything about saturation, fake it.
I mean, you can always assume that you can split one long exposure into several small ones.
Yeah, but
and
since I really don't know that camera, what is I couldn't find the specs for that camera, so I don't know. So assume that you can integrate as long as one. And see if you can get to the specs of Cisco. Everybody did. So,
Okay, questions? Okay.
No, good. Yes.
How much does a BTF filter cost? Pre-filter cost?
Ah, pre-filter. 20,000?
Okay.
No, not too much actually. It doesn't cost too much, but
So you can come with your own, like.
well, count with your own then. Maybe not.
I mean, come where? Because you're not gonna go anywhere.
You're not gonna
Plus calibration, polarization.
Yeah.
Come to that room in the other wing with your own filter. Look at the
You
screen.
could do that at the DST. Here, a little less. You know, the idea is that the instrument lab is kept as stable as possible. So you don't have people going in now. Don't let me tweak that. No. Yeah. So, but about 20,000, I think. They are bigger. I don't know if they are the usual 2 inches. I think only if they are larger. Okay, thank you. Sorry for going so long.
No worries. Okay, very good. Yeah, your homework will be up on until the end of the week, and Thursday we are starting with the second part. So we are moving away from the instruments. We are going toward the physics and the diagnostics. Yeah. See you in 2 days.
You want to ask anything? They could speak if they want to.
I think they hear us very well. So they will. Amazing. Yeah, you stop sharing, and I try to stop recording.